Hi, so my name is Alptoka. I work on the Clang front end, and I'm going to be talking a bit about what we do, why we do it, and some of the things we might be doing soon. So the talk is in two parts. First part, I'm going through these main topics, and after that, we're going to look at some of the current topics that we need to solve in the front end. So we're going to be looking at things like optimization attributes, passing things to the back end, a few topics that have been interesting recently. So let's see. Okay. So these were the questions I was asking. I've been asking myself some of these questions. I'm not actually a compiler engineer by education or training. I do compilers because I need to solve a problem. I write software, I write web browsers, that's what I do. I work on the WebKit browser engine, and we have a lot of C++. We need to compile huge projects, and we need to not only compile them, we need to refactor them, we need to do stuff with our code. And we were hitting limitations with GCC, with MSVC, all the things that we were using to build WebKit. It was becoming a barrier for day-to-day work. So as you do in open source, we decided to take a look at alternatives, options, and I had a look at Clang a few years ago, and a bit of an adventure started then, kind of a bit of a distraction even, I suppose, from the real task of fixing browsers, and we ended up doing a lot of stuff with Clang. We started out in-house, and we moved towards upstreaming. So at the moment, we're in upstreaming mode. We're putting patches back into open source, working with the community, and I'm helping maintain the parser of Clang. So what can we achieve going beyond compilation? As I said, it's much more than just a compiler. It's an entire tool chain, it's got libraries in it, and these are the things that make Clang special. You can actually use it to build your own tools that refactor, rewrite stuff. Why did this happen? There's some politics involved. In some sense, maybe other compilers should have got there earlier if they've been around for longer, but that didn't happen. So I'm going to have a look at that. And what other things can we do to make life easier for developers? So right now we have a compiler, we have a library that lets people plug it in, but maybe there are things we can solve. We already know about expressive diagnostics. I think I'm not going to go into expressive diagnostics because everyone's spoken about that, and we know that already. There's other stuff to be looking at. So, and finally, I'm going to have a look at the social change idea. It's a compiler. It's just another tool. How could that possibly create social change? Well, insofar as everything goes through the compiler, it has some significance. And this is something that struck me when I started working, I suppose, on the front end. And you realize that when you fix one issue here, 1,000 more projects work. There's such a long tail of projects that you can support. Even in the early days of Clang, because we were doing that quite a few years ago, you would see more support, more applications start to compile. You see that it's actually happening. So it's been built up quite recently, over the last few years. It's a fresh start. It's a compiler written in C++, so it self-hosts, it compiles itself. So I'm going to give a bit of background. How is it built? What's inside? Just so you know what's going on. We have something called lowering in LLVM. And people always ask, what is lowering? It comes up a lot. And lowering just means moving stuff from one representation to another, usually lower level one. So we start at the top. We have source code goes in, C, C++, Objective-C, Objective-C++, various variations on that, different language standards. Goes in the driver usually. The driver is a component that is GCC compatible. It takes the same flags it has a very familiar user interface. It's a separate process, and it kicks things off. That's the thing you pass your command lines arguments into. There's also another driver. There's at least 2 drivers at the moment in SVN. There's Clang CL, which I'll tell you about in a bit. That's the Microsoft Visual Studio compatible driver. So we've got 2 drivers, and then these call into the front end. Despite its name, the front end isn't at the very front. It's in between. Don't ask. And the front end is the brains. It does the cool stuff. It parses, it does semantic analysis, it does stuff that you would consider a compiler, at least if you're a front-end kind of person. That's the meat. And that ends up lowering down to IR. It has something called codegen, which is actually IR generation. And that creates your more familiar intermediate representation of your code in LLVM format. And then the driver might go ahead and take object file output, pass it through to the linker, and through that pipeline, you go from source code to basically binaries you can link, you can run. These are executables, these are things we know of as compiler output. So a compilation actually invokes various processes. It's not just one app. It calls itself from time to time, it calls linkers, it calls other things, it calls assemblers sometimes. It's kind of a closed box. It decides when it wants to do it itself, when it wants to call out into another tool. So if we dig into the front end, this is the front end, or an approximation of that. And there's more lowering going on here. Everything's always percolating downwards, down towards IR. And you can see, again, the source code goes in at the top. You lex, you parse, you do your semantic analysis. So lexing means turning characters into a stream of tokenization. Parsing means taking those tokens, turning them into something of an AST. Through, in Clang, the semantic analysis comes first. So the semantic analysis builds the abstract syntax tree. Abstract syntax tree is a tree of your source code. And there's also the static analyzer, which also gets called in from time to time by semantic analysis to provide more expressive warnings and diagnostics. So through that pipeline, you end up, again, at code gen, at IR gen, and you've got more or less there to a binary output. And then LLVM does its stuff, which probably a lot of, there's a few talks today about code gen back in the LLVM backend. So I'm going to focus on the front end here. These are the actual full list of modules. So you can see there's various things, but they map to the concepts that we're interested in. So this is the cool stuff. This is the exciting stuff that makes Clang clangy and nice to use. They all do kind of the same thing. Well, the ones at the top at least. Some of them use each other. These are facilities for using compiler internals to do cool stuff. So there's tooling, libtooling, which lets you roll your own compiler. You can actually, with I think 6 lines of code, 8 lines of code, you can actually write a small program with your own main function that lets you write a compiler. It takes in command line arguments and it generates output. There's libclang, which is the stable C API, which uses C index, and that libclang lets you go through your AST. It lets you look at your intermediate representation. It's a stable API, so applications can use that. IDs tend to use that. It's maintained separately, so sometimes it needs to catch up with the core internals. If for new language constructs, it's sometimes behind. But if you weigh that up against it being stable, that's pretty cool. And a lot of applications use that. Also, language bindings use libclang to support access to the AST and indexing from language bindings. So apart from that, there's also plugins. Plugins that use the full internals of Clang. They're also kind of tricky. They don't always work. They're less maintained. There weren't tests until a week ago. So plugins right now, aren't used that much because it depends on internal representation. It depends on the internal API of Clang. So people always ask on the mailing list, which one should we use? There's all these options. Generally, tooling or libclang are the viable options for applications embedding Clang. So why do all of this? I suppose we want access to these internals. We want to be able to see inside our code. We want to be able to manipulate our code. If all we want to do is compile software, then sure, there's already compilers out there. But really, there hasn't been something on the scale in open source. There were a few very interesting academic projects for various tasks like refactoring or individual problems, but none of them really pulled it all together. So it makes sense to take the compiler that's there and also provide access to external applications and these various use cases. So there's been a bit of a craze in Clang. Nobody knows quite why, but there's some good reasons why. So a lot of people have been pushing for compatibility with Microsoft Visual C++. It's kind of it's a fever. You get into it in a big way. It's like you feel this rush. Wow. But this is probably maybe closer to a motivation for Clang developers. You know, we built this thing. It passes standard stuff, ISO C++, C++ extensions. Yeah, sure. C was there first. Some other standards, some interesting things like parallelism, or you have GPU specializations, which are C-like languages. That's where the name comes from. So it's C-Lang, Clang. And there's something missing. There's a bit missing in the corner. And that's the long tail of Microsoft Visual C++ applications. So what we really can achieve by this is building real software out there, a huge amount of projects that aren't currently portable to Unix. So that's one advantage, one thing that we get out of it. And the second benefit is the other way around. We get to put the compiler on Windows, and we get to give developers on their native platform a better experience. And both of these are really compelling. So porting, we get porting to Unix, and we get to help developers actually port their Unix software to Windows. So that's 2 for 1. That's pretty neat. So it's a bit tricky. There's various things, fun things in Microsoft Visual C++, but it's been coming for a while. It's more than Windows support. It's not just porting the compiler to Windows. I saw a comment on a forum somewhere saying, why is Windows support a big deal? Surely if you port the file system access, then it will compile. But it's doing something different. It's not really Windows support. It's MSVC support, and we need to be more clear about that when we describe it. And the changes, the differences are all through the stack, from parsing. There's various things that are different in parsing. There's the ABI is different when you're generating IR. There's all kinds of things in semantic analysis that need to be different. So it's a bit of work, and it's a major impact on the code base, but it's been coming together, and it's very close now to bootstrapping, to self-hosting. So it would be able to compile using Microsoft headers on Windows, which is quite exciting. It means you've got a drop-in replacement at that point for the Microsoft C++ compiler. So that's probably very close. And I mentioned this second driver that exists, and that's what enables the seamless integration, the drop-in integration. ClangCL is a command line compatible driver that you can pass the same arguments, the same arguments as cl.exe, and it does the same thing. From input to output, matches Visual Studio, C++ compiler. So, big problem, but you can face up to it. And the thing we're doing is we're trying to be like them, I suppose. That's the only way to not defeat, but to overcome these challenges. So, how do we do this stuff? The parser, that's the bit I'm probably most interested in. It's handwritten. This is something that shocked me. The first time I saw the Clang parser, I said, WTF, why is this, it's huge handwritten parser. We're used to, when we need parsers in other projects, we write descriptions of the grammar, of the syntax, and we let a tool generate our parser, even our AST usually. So why would someone go and write most of this stuff by hand? But a couple of years later on, it makes perfect sense. It's really nice. It's beautiful. It's kind of like the parser is like a dusty gem, you know? It's beautiful inside once you get used to it. Until you rub the dust off, it's a bit scary, but it really works, and it lets us do things that you just wouldn't be able to do. You can't even parse C++ with a generated parser, at least not one that's mainstream, that's out there. So it makes a lot of sense, and it lets you experiment with things. You can generate diagnostics, you can throw in a bit there. It's very easy to get started and just start editing a bit of code that does a bit of parsing and fix a bug. It's very accessible. And it's unified. That's something else that would be hard if it was generated. It actually uses the same parse rules to parse all these C-like languages. So C, C++, Objective-C, and these other extensions all go through the same parser engine. And it's used to be completely decoupled from semantic analysis and the AST. Now it's still fairly isolated. So it's a parser in the classic sense that it parses stuff and does callbacks into a different layer. So it's still clean, it's still, I suppose it's still friendly to compiler engineers who are purists, who have that separation in their minds. And there's semantic analysis. There's the brains. That takes the stuff from the parse and turns it into a fully constructed AST. The Clang AST is constructed, so it contains the result of the semantic analysis within it. So some other types of syntax trees are just syntax trees, and then you have to have a separate analysis. In Clang, the analysis happens while building the AST. And this is quite handy, especially with C-like languages. You can usually do semantic analysis as you pass in order. So it's elegant to just build up your tree as you go. So there's a few things there. I mean, it's another dusty gem that you need to polish from time to time. There's a lot of, well, there's a bit of copy and paste going on there. Just because people, they have a need for a new language feature. And what do? They have a look. They see which other part of the implementation does it, and they try to sneak in a bit of a copy and paste. And the review system is really good. Patches are reviewed. Everything gets looked at. But the one thing that's really difficult to catch when someone's submitting a patch is actually code that exists somewhere else in the tree. So this tends to get missed. And as a result, you get these slightly awkward patterns in the parser, so in semantic analysis and in the parser. So these are the only annoying little quirks, really, which is good because I've worked with a generated AST and system, and you get fundamental problems when you're actually generating your parser from a description. You have tool problems. So the fact that the annoyances with the parser, with semantic analysis, are basically things like this, like small annoyances, is pretty good news. That we're happy with what we have. We're happy with the infrastructure. It's basically okay. So the question is, I suppose, what stuff can we do now? I mean, we have the basics down. We have we have it working. It's been self-hosting for a long time. It's going to work as a drop-in replacement for Visual Studio pretty soon. So what are the interesting things that we can do with this? Are we competing with something else, or is it just a project unto itself? So there's a few things. These are more my brainstorms, things that might work, might not. I need to ask, I suppose, back-end guys for a few of these questions. But there's some basic things here that we're looking at right now, just to see if we can take shortcuts. Because we've noticed that a few things are running out of process when they could be running in process. It's very recent. It's not a big deal. But maybe we could just shave off a bit more by actually running more of the compilation in one process. This matters perhaps more on Windows, where process invocation is rather slow. So there's kind of an idea somewhere in my mind that you could actually build your entire project with one compiler invocation. How that's going to work, it's some way off. It may not be clear exactly how that ties together, but the idea to begin with is that we might at least not invoke the front end from the driver separately, because they're in the same binary. So we can just swap little things, and things like that tend to get noticed, tend to get missed while we're busy micro-optimizing the parser or finding huge things to tune in semantic analysis. We forget that actually the driver is doing fairly big operations with fairly few lines of code. So there's some interesting opportunities there, and we need to measure. We need to get some numbers there. So it's just one theory right now that we could shave some time off the build there. Modules is a big one. Modules are basically the culmination of precompiled headers. They are the same AST, the same internals that you get when you're analyzing your code, when you're running libclang, but they persist through invocations. So there's a serialization format that actually, when you've compiled, when you've turned it into an AST, into a semantically analyzed result, you can actually cache that to file, and there's more to modules than that. Modules also embody things like headers, includes. There's a lot of work behind modules, but it's starting to come together in a big way. I think macOS recently shipped, Mavericks had some modules in the headers, so this is coming together, and that's going to be a big speed up, because it means you don't have to parse. It means you don't have to do semantic analysis for a lot of the headers, and it means you can just spend more time compiling your code. And the headers don't change much, so it's not a big problem. If they change, you just rebuild the modules. They're cached somewhere. Another interesting one is actually just caching some things like stats, file access through invocations. Once we have things perhaps in one process, then we can start to look at see what can we now reuse between each file that we compile, because we don't need to restart it. So these are some possibilities to just kind of cheat and shave a few seconds off, or a few split seconds off compilation. And the last one is my little crazy idea. That we could actually go through the JIT to do things like compile time evaluation. At the moment, we have a great JIT engine that a lot of projects are using in the back end. It can do all sorts of things, but we don't use it. We don't actually use it ourselves in the project, as far as I'm aware, for any part of the compilation pipeline. So it increases quality a lot when you use your own tools. You get used to working with them, you improve the API, you fix bugs. So some excuse to use the JIT in the front end, I think, would be really cool. So this is an idea right now that's not really manifested in anything, but if we can find somewhere to use that, that could be pretty neat. So these are the little tricks that we might be able to pull off to kind of unconventionally get some faster compile times. Another thing is, I mean, if you can see the problem in this code. Yeah. Well, that's actually a problem. So One thing we're not doing, that we haven't done at all, is accessibility. A lot of projects, I think, a lot of projects here, you'll find, if you've been to other talks yesterday, people actually are working, they're putting a lot of resources into accessibility, APIs, SDKs, ways to access the thing, whether it's a document, whether it's LibreOffice, or whether it's the browser, we expose the DOM. Everything, we try to expose these in a way that people can see if they don't have great vision, if they have maybe difficulty interacting with their machine, there are facilities available to them. Clang is an application. It is an end-user tool. And there are lots of possibilities here. Accessibility is something that's very natural to represent trees in. So the fact we have a tree is already some way there to actually representing accessibility. Using accessibility toolkits like Universal Access on Mac, or ATK if you're into GTK technologies. There's all these possibilities to give people more access to their code, to let people code, manipulate their code as well. So it's not just the AST and the tree of that, but things like code completion would also make it easier to interact with your code, to edit your code. And there's a great code completion engine inside Clang. So the tools are there. Diagnostics, they've got tokens in them, they've got funny names in them. If you try to pipe it through a speech system right now, it doesn't do much. But if with a little annotation, that could go a long way. So that's one of the things I think would be cool if we can maybe just stand back and say, hey, we do actually ship something that people use, end users use, and that IDs use as well. We shouldn't expect IDs to go and try to do this. Editors, we shouldn't expect them to do accessibility because it's hard work. And I think this is one thing that we could do. This is probably my personal view on this, because I've come from other projects where we spend a lot of time on accessibility. So that's the kind of thing that could be a nice goal at some point. It's not right there yet. This is something that's moved forward a lot. The Linux kernel. It's basically compiling now with Clang and without much external help. So this has been a long time coming. The LLVM Linux guys have a talk, I think 11 o'clock, if I got it right, today. And there's a big effort, a lot of testing and infrastructure. There's a real push to get support for the ability to compile the Linux kernel with Clang. And this has been going on for a few years now. So this isn't a new thing, but it's just reached some kind of, I suppose, fruition. And some interesting patches have happened recently. So I think David Woodhouse's kernel guy, he's got involved. This is exciting because it means users, they can just come in and they can start contributing. And this has happened with a few projects. This has been one of the visible cases where people had a need. They needed to get support for something, and they couldn't get that out of, whether it was GCC or MSVC, they couldn't get that thing. So when they came to Clang, Clang was different. Clang welcomed them. Clang welcomed their code, provided the necessary review, even though not many people need this. Not many people need a 16-bit code gen. Nobody really said, this is not what we do. Nobody said, we do not want this. We said, what's the use case? And that's cool. And that most of the 16-bit work went on in LLVM. A tiny bit is in the Clang front end, but I suppose the main use case is through the front end. So what they're able to do is replace a lot of handwritten 60-bit bootloader code and various facilities in C, which is nice for their use case. The other thing that's come forward is it's close to, I think, passing all the assembly. So using the integrated assembler, and this is, again, it's an LLVM thing, but it goes through the Clang driver, and it's worth mentioning that that's the way it looks to end users. It goes through Clang, and with those things done, it's basically able to build and boot. There were a few other past things, a few GCC compatibility features that were necessary, but it's getting there, which is really exciting. It's going to hopefully affect a lot of developers who want the features, and also with the tools, they'll get to do more security testing, do more various things that they couldn't do before, because they only had a partial view of their code. So, yeah, there's a few more nits. I mean, I mentioned some of these, I think, when we were looking at semantic analysis and the AST. There's some tidying to be done. The type system needs a bit of love. We've been aiming for getting close to the standards and what they describe. So just a bit of internal refactoring to make it match up to common terminology. And I think when the internals of a compiler actually represent the specification, that's really good, because it's immediately accessible. You can read the code and you know what it means. So little cleanups. I'm into my cleanups when I'm working on the front end, but they're actually done for a reason. It's to make the code, you read the code, you see what it's doing. So these are kind of minor changes that are going on to tidy things up as well internally. But Clang is also defending software freedom. I mean, there's been a few complaints recently, and these are unjustified. Clang is all about, well, it lets a lot of people use free software who normally wouldn't be able to. And I think that qualifies as a lot of the definition for free software in the traditional sense. So while people have different motivations working on the project, this is actually an end result that we've got people no longer using MSVC. They're now using Clang. They're getting more involved with the community. They're joining and doing things that they normally wouldn't have done. Companies that had proprietary tool chains are now switching to an open source compiler. I mean, how is this? This is defending software freedom. And this is the first freedom, the freedom to do what you want with the code. And that option hasn't always been available with other compilers. Whether it's a license fee, or whether it's some other restriction, or just the attitude of that team, other compilers haven't let you do crazy stuff with your compiler. So I think there's some amount of this freedom number one, which is to do what you want with the code. Take it and run with it. And if it's good, then that's good, and it'll get taken back. With something like, say, GCC, you can get vendor patches, you can get companies, they might do code dumps, they might do code drops, but how many of those actually get integrated back? I'd be interesting to see how many proprietary branches happen of other compilers, and how much of that comes back. I mean, we see companies sending patches because they love sending patches. They want to work with the community. So it seems to work really well. It's kind of it's an implicit copyleft, I suppose. You're meant to send back patches, and you're meant to work with the community. It's not enforced, so people don't have to send back contributions to the project, but they end up doing it anyway, because they want to work closer to what we do. So effectively, we already get the software freedom. And there's also a slightly stronger interpretation of software freedom, which is freedom number two. And this one is, I suppose, nobody can tell me what I can and can't do with my compiler front end. And, you know, if we want to refactor, that's great. If we want to do plugins, that's great. So, on a very basic level, we need to do this. If we're going to move forward technology as a whole, we need to be able to manipulate the code. We need to be able to analyze the code. Everything is source code these days. So we need this basic freedom, and we need to fight for that. We need to stand by that. We don't get that with other projects at the moment. So this is the hope we have. Community 2.0 is probably where we are now. We're getting a nice kind of environment. We're getting new contributors. Things are really building up. The project is very successful. And there are introspective questions we need to ask. These are things that happen day to day, I suppose. These are challenges that developers face. And I'm sure there's more. These are some of the ones that have come up recently. So when there's trouble, when someone posts something questionable to the list, how do you respond? Do you have a canned response? Do you say something? Or do you just ignore them? Do you get angry with them? There's no real clarity on that, because it's a meritocracy. Everyone codes and they're trusted and they reply to contributors. So it's slightly informal like that, and that can occasionally backfire. It can give a harsh first impression to people writing patches. These are things we need to keep in check. We need to make sure it doesn't turn into a vicious project where we don't welcome people who are just trying to contribute. So this is something I care about, because it's the right thing to do, to welcome people to your work and then see what they've got to contribute before really going against that. So the other thing that's come up is sometimes you get people who want to write documentation, or they want to do something else in the code, and we're very tuned for reviewing patches to the compiler, but we're not very used to dealing with people who want to give something else, whether that's resources, hardware, time, or some other facilities. So in terms of community, I suppose this is LLVM/Clang, we don't have a framework for dealing with some of these things, like documentation. Someone was writing great documentation recently, but there wasn't really anyone who was able to give direction on those patches, and we ended up without documentation because it didn't work out, the documentation wasn't quite right, so we miss out on very important things in the toolchain because we're so focused on code. We're compiler guys. We don't even know how to bring these people into the fold and say, thank you, let me refer you to the documentation guy. We don't really have that, and we miss out because of that, and we have to write docs ourselves because of that. So it's something we can do to solve. It's growing. It's a big code base. It's a bit uncomfortably large in places. It's the nature of something that's handwritten. It's the nature of a project that does so much. But there's a core of maybe 30 to 40 active developers on Clang at the moment. This is based on a 1-month analysis. It's a January analysis, so it could be 30 to 60. It could vary. The 1.5 million lines of code, it's a lot of code, but a lot of that is tests, so it's not quite so scary in reality. There's a bit of a plateau happening there, which I'm hopeful is the case, because it would be great if we could keep things trim, I think, at this point. It keeps growing, only gets bigger, but maybe we can flat that out there. So there are 500 commits per month. The commits, each one is usually a significant commit, a feature, or a fix of some kind. So once a patch gets reviewed, it gets landed. That's how it's meant to work. And there are slightly more deep questions, I suppose. And these are the questions that are sometimes that we LVM, Clang, we discuss with each other. Some people might know better than others. There are some questions. What if something goes wrong? What if there's some kind of patent scare, or something, someone says something they shouldn't, and someone gets picked out? What do you do? And there's a bit of this is a weakness. I mean, I'm not just being the salesman here. I'm trying to find potential things that we might have trouble with. And at the moment, there's a project, there's a community, but we don't have an absolutely clear idea of what's going to happen. So transparency is good. It's very good on this project. Could it be more transparent? Always. I believe in sharing and explaining how things work, and that's not always there. With some things, it would be useful to have a bit more clarity. So one of the things that's been discussed a lot is there some way to maybe provide a separate entity that can actually deal with these, whether it's menial tasks like infrastructure, well, not menial, but providing the funding for infrastructure and providing essential sports, events, that kind of stuff. Right now it's done by people who care a lot and they put in the time. Could that be formalized? That's one of the questions. And then could there be some kind of support, at least to review things with a legal point of view? These are other questions, and some projects do have foundations and they're very successful. Others don't, and they also do well. So it's not necessary, but I mean, one thing we could do, this is a hypothetical thing, and it's come up a few times, is maybe some kind of LLVM foundation that would also be useful for the things we're seeing in Clang at the moment, some of the discussions. And then we could also rename the CFE compilers for everyone, because it used to be C front end, so that kind of backronym works there. But you know, it's my patch, my idea, if I send it to the list at some point. But I think something like this is going to be useful at some point. We may need it, and it's better to be prepared. So it's difficult. There's a lot of questions. This is a prickly kind of thing to discuss, but it would be better if everyone got involved and did it transparently, rather than having such a thing done unilaterally by any single organization or group of organizations. So there'll be some value in discussing this out in the open. Community has also been growing in other ways lately. So we've got LLVM Weekly, which is great. It also covers Clang stuff. I really enjoy it. I wait for my LLVM Weekly newsletter. And this is this community feeling that, you know, it's LLVM has been around for years, but that community feeling is really just coming along really nicely now. And there's a bit of a plug, Planet Clang, which is a blog aggregator. If you do anything C++y and Clangy, get on Planet, send the mail to planet@clang.org, and we can get your blog up there. I'd be really interested to read more about what developers are doing on Clang. It's already a nice story. There's only, I think, 4 of us or something. But it's a fun story. It tells the story of a compiler. It tells the story of the people who do what they do. And it's our world. So if you do blog, or if you're thinking of blogging, it would be great to maybe have your thing there. And the rules are pretty lax there. You know, you don't have to be a committer. You don't have to be this or that. External projects are also welcome. Subgroups are also welcome. If you do something Clang related or LLM related, that's a good place to go. We're going to be looking at possibly a few things that have come up recently. There's been a lot of interest in providing attributes and pragmas to communicate data to the back end. So this is something that's been requested for a while, and we haven't been able to really contact it on the list for whatever reason. It always gets delayed. So that's something I'm going to call up Renato for in a second, and we're going to have a look at options with that. So we're just going to pop that in here in the few minutes we have. So yeah, thank you.
Yeah, so we have a couple of minutes for questions, so just feel free to ask, and if you can just repeat the question for the microphone.
Sure.
So it looks like we'll have a use CL Clang for a cross-compiler very soon. To use our fastest build platform to build for our slowest build platform.
So cross-compilation was the dream. It was the idea. The front end hasn't quite got there. The driver, they have theoretical cross-compilability, but this idea that you have one binary that then hits every target hasn't quite materialized. So there's some need for fixes, a few fixes, but that's the way it should really go. I think there's one project that's actually done a bit of work there. Was it ELCC? This gentleman has taken Clang and also provided headers and libraries, so he's reached that point where I think he can target more things. So it'd be nice if we get stuff upstream or similar stuff upstream. So it shows it's possible.
Very nice, about 3 times the fast installation I was called on it.
Yeah, it should happen. Yes?
Very important was this slide for the LLVM foundation. 3 points that are about continuity effect. About continuity of infrastructure and so on. Yeah. This kind of items exist also among other people that generally are involved in building software, so I was proposing should you think of something like a build foundation?
Okay, so the question, right. The question is, should we generalize the foundation? Instead of an LLVM foundation, should it be something that covers more topics like building infrastructure in general, maybe covers other tools? I think that could be really interesting. There are some things like licensing. The licensing terms we're very used to having non-copyleft, for example. So that might create an artificial restriction on other projects that are less strict on that topic. So I would be more worried that such a thing would maybe have a negative impact on the other projects. But I think if they follow the general philosophy and roadmap of LLVM, that could be quite interesting. It would be great to get people talking on that topic. So yeah, I think it's just good the ideas out there.
I think there was this lady on.
Ah, right.
Yes. With respect to the resource usage that we're running a project that looks at energy consumption.
Right, yeah.
We've got some proposals as to what would include countryside and how we can connect this to weather.
Brilliant, yeah. So it's great that you actually have some invitation. Are you using they're using annotations, pragmas to pass information to the back end. Their use case is, I think, of power consumption. They want to create code that's more efficient with power resources. So it's kind of an optimization problem again. And one of the ideas we had is maybe that they have something that we could reuse in terms of a language description for pragmas. We've got it up there. We've got time for to look
Yes,
at some code. Yeah?
5 minutes.
Okay. Let's put it up and have a look. That would be interesting.
Oh, okay. Yeah.
So,
Wow. Okay.
okay. But if it's
So yeah, it's a presentation.
a
couple of
I see.
I don't think we have like so much time for presentation.
Okay, yeah.
But we have in the afternoon. We actually may have an empty slot.
yeah.
You might want to.
So,
Just see
that bit.
that session, yeah, only that.
Okay.
yeah, but yeah, I'm just thinking just
Maybe
for
just one.
yeah.
Okay. Okay.
If Karen has seen that you.
Wait.
I'll hold it, please.
Yeah, but. Right.
This is really important to us because
Okay.
yeah. So this is C++ 11 attribute that we use.
Yeah, it's quite similar to C++. So what we are trying to do is to annotate the code for several resource analysis and function attributes. So, for example, the first one, we're trying to say that that specific variable at this point of execution should be less than 10. And we have another annotation saying that that specific variable should hold through the whole program execution and be lower than 10. Also, you can specify the max loop iterations, and you can do that kind of annotations for any kind of, also for probabilistic approaches. So branches, so you can say ignore the true case of a branch. Or also you can do it for functional properties. So for example, if you want to say, I don't want this branch to take more than this energy, we are currently doing a resource analysis using some energy models, combine them, and then we're going to have a presentation later today on the LLVM demo. I think it's around 4.
Okay, great. So that'll be really interesting to see if we can take that and generalize that into the same problems that others need to solve. There's a lot of people have been asking for this, so give it more visibility. That's brilliant. I really like the stuff you've been doing. So, awesome. Great.
Okay. So we have still 3 minutes for a couple of more questions. So there's one.
All right.
there.
Windows support very interesting. It's going to be possible to compile drivers and
Is it going to be possible to compile drivers, Windows drivers?
Windows drivers and also
So-
get them signed.
get them signed. The first bit I can answer because it's already happening. There's actually two Microsoft modes. We've got Microsoft compatibility and Microsoft extensions, and people are actually compiling Windowsy drivers on Unix. So they're using this to port Windows drivers to FreeBSD, to Linux. That's pretty cool. The question is, does it work the other way around? I've spoken with some people from ReactOS, who are very close to building some drivers. They need one more parser feature. They need, I think, nested functions. But basically...
No, they don't.
No, they said they need...
No, they don't.
I haven't seen it. Nobody needs nested functions.
It's not going to happen.
Yeah. But it seems they're very close, so I think it's going to happen as well, naturally.
Do you also target some other ABIs, like for example Sun, Solaris, or so?
No major APIs other than I think the ones, the MSVC and the standard Titanium. So
Patch is always welcome.
yeah,
If you have them.
we'll accept them summarily. Yeah,
So we could port.
yeah.
So yeah, we have 1 minute left, so I think there's time for a very last question. And
Can't you use your insight in the code with the AST to find duplicated code? Because that
I was hoping someone would say that.
Yeah.
We have analysis. We could do that. We could use plagiarism detection.
Yeah.
We would have something useful for universities as well, I suppose, that they could detect code. Or even if you want to find nasty code in your code base, you could actually detect patterns. So that would be really neat if we actually dog fooded there. If we consumed our own dog food and used our own tool again to find patterns and summarily kick people out of the project if they suddenly copy paste code. That would be awesome. Yeah, that would be freedom. Good idea.
yeah, wonderful.